It is my pleasure to introduce our next speaker, Manasha Vempati from Louisiana State University. The title of her talk is Boundedness and Compactness of Bloom Sparse Operators.
I would like to start by thanking the organizers for giving me this opportunity. As it's mentioned, I'm going to talk about the boundedness and compactness for Bloom sparse operators. The motivation for looking at Bloom sparse operator comes because of the pointwise sparse domination that we have for the commutators of Calvin-Zygmunt operators. So since that was our motivation to begin this study, I'm going to start by discussing a little bit about the boundedness results that we have for the commutators. So for any linear operator T, we can define the commutator as this operator Bt as Bxtfx minus T acting on Bf. The question that I'm trying to discuss today is when and with what quantitative dependence the commutator is bounded between either weighted or unweighted LP spaces. So, a little bit of history about this problem. I think this was covered in Nathan's talk in the morning, but I would like to go over it another time. So, this result about the boundedness of commutator on the LP spaces was first given by Koifman, Rochberg, and Weiss in 1976. And this was given for the Calvin-Zygmunt operators such as Hilbert transform, Riesz transforms. And the result they gave was that the commutator is bounded from LP to LP if the symbol B is in the BMO space. BMO space was also defined in the morning, but to just recall what was said, it's a space of bounded mean oscillations where you can think of these as locally integrable functions whose mean oscillations are uniformly controlled over all cubes in the space. Once there was a result about boundedness, it was natural to think about the compactness of commutators, and this result was given by Uchiyama in 1978. And this result discussed the compactness in terms of the symbol being in the VMO space. So the result says that the commutator is compact on LP spaces if B is in the VMO space, which is called the vanishing mean oscillations. In the Euclidean setting, vanishing mean oscillations is equivalent to the closure of compactly supported smooth functions. But in general, the vanishing mean oscillations means that the mean oscillation basically vanishes in some regimes, like it could vanish on small cubes, very large cubes, or when the distance from a fixed point is becoming large. So the previous two results that I've mentioned regarding boundedness and compactness are discussed when P is in between 1 and infinity, and it's natural to think about the existence of any weak type results here. And it turns out that the commutators do not really satisfy the weak 1-1 type estimate. However, we have the weak L log L estimate here. So here you see on the right hand side this Young's function, which says that the commutator basically takes this L log L space to L1 infinite, the weak L1 space. And this result was given by Perez. So the results that we have previously seen were in the unweighted setting, and the interest to look at these results in two-weight setting came up in the works of Bloom, where Bloom discussed the two-weight commutator result for the commutator of the Hilbert transform, where it was shown that the commutator is bounded from LP weighted mu space to LP weighted lambda space if and only if B belonged to a weighted BMO space. So here the weight nu that you see here is coming from mu and lambda, and it's given as mu over lambda to the power of 1 over P. This result, as I've mentioned, was given for the commutator of the Hilbert transform, but this was later extended to the commutators of Riesz transform and some other Calvin-Zygmunt operators, even the higher order and sparse forms by these people, Holmes, Lacey, Vick, Lacey, Spencer, Moyne, to name a few. So our result basically discusses the compactness criteria of Bloom's sparse operator. So here Bloom's results and the other result I've mentioned discuss the boundedness, and ours is a compactness result. And we discuss the compactness of sparse operator in this Bloom setting because it's motivated to finally discuss compactness result for commutators of Caldron-Zigmund operators in this Bloom setting. So we do have the sparse domination for Caldron-Zigmund operators by sparse operators, which was given by the works of Lacy Lerner, and the sparse domination for commutators was given by Lerner, Ombrosi, and Rios. So this is a result that discusses the sparse domination for commutators. So here we've considered a Caldron-Zigmund operator T. We are looking at the commutator, and we're saying that there is an n such that the commutator is bounded from above by the sparse operator and it's adjoint from the sparse collections from 1 to n. Now, let me discuss the question that we've answered in our work. So for p in 1 to infinity, lambda 1, lambda 2, the AP weights, and nu that's defined by these weights lambda 1 and lambda 2 as lambda 1 over lambda 2 to the power of 1 over p. We consider B in the weighted VMO space and we discuss whether the Bloom sparse operator is compact or not. And we've addressed this question in the setting of spaces of homogeneous type because it's more general than the Euclidean setting, and the harmonic analysis beautifully extends to this setting. So just to discuss what the space of homogeneous type is for anyone that's not familiar with it, we say the space X d mu is a space of homogeneous type if D is a quasimetric on X and mu is a non-zero measure that satisfies the doubling condition. So quasimetric is essentially a function that satisfies these properties where the first two properties are similar to what you expect for a metric. On a metric space, the third property is the quasi-triangle inequality where you have this constant A naught that is bigger than or equal to 1. And a measure we say satisfies the doubling condition if there is a constant that's dependent on this measure, such that if you look at a ball of radius 2r with center x and you look at its measure, then it's bounded by this constant c mu times the measure of ball with center x with radius r. And these balls that I'm talking about are given with respect to the quasimetric. In our proof, we also deal with the system of dyadic cubes. Since we are in the setting of space of homogeneous type, the dyadic system of cubes construction is taken by the construction of Heitinen and Kairima. And to discuss that, it's a little more technical to write down these cubes. So I've just mentioned how these cubes behave in the Euclidean setting because the properties are kind of similar to what you would expect in the Euclidean setting for the cubes on space of homogeneous type. So on Rn, a dyadic cube is a product of dyadic intervals of same length. For example, if you have k and z, a dyadic cube of side length 1 over 2 to the power of K is of this particular form. And the fundamental properties of these cubes is that if you have two cubes and they did intersect, then one of the cubes is going to be contained inside the other, otherwise they would not intersect. And if you fix K, you could write your space as a union of the cubes coming from that dyadic level. So these properties are what you would have when you have cubes on the space of homogeneous type 2. As you saw in our question that we were trying to look at, we were considering weights belonging to the Mukin-Hopf AP class. So let me also define what these weights are. So we say a weight W is AP weight if it's non-negative locally integrable function such that the AP constant, which is this supremum over this integrals, is finite. For p equal to 1, we say that W is an A1 weight if the Hardy-Littlewood maximal function put on this weight is less than the W of x almost everywhere, and A infinity weights can be considered as a union of all of the AP weights for p lying between 1 and infinity. And in our setting, our results is given in terms of weighted BMO space. To get to that, I would first like to define what weighted BMO space is on the setting of space of homogeneous type. So we consider some A infinity weight W, and we say that B is in the weighted BMO space on the space of homogeneous type if it is locally integrable, and the BMO norm that is given as the supremum over this oscillations is finite. Here the supremum is taken over all quasi-metric balls B, and in this definition this B with the subscript of the ball just means the average of this function B on this ball, and this is the mu average, where mu is that doubling measure that exists on our space. Now that we have the definition of BMO spaces, we can discuss about VMO spaces, which form a subset of the BMO spaces. As I previously mentioned, VMO spaces have these properties given here by 1, 2, and 3, where we say that the oscillation basically vanishes in these regimes where you either have a ball that is tiny, a small, or you have a ball that is large, or you have a ball whose distance from a fixed point is huge. So in all of these three regimes, your mean oscillation kind of vanishes, and this is a property that we use to characterize our compactness. And since we are talking about Bloom sparse operators, and I haven't defined what these operators are, so let me also quickly define a little bit about the sparse collection of cubes and the way we define the Bloom sparse operators. So given eta between 0 and 1, we say a collection of cubes S is a sparse collection of cubes if S is in the dyadic, S is a subset of these dyadic cubes. If for every cube in this collection S, there is a measurable subset EQ, which is large, in the sense that the measure of EQ is bigger than eta times the measure of Q. And another property that these measurable subsets have is that they only have a finite overlap. And now that we have the definition of a sparse collection of cubes, we can define sparse operators, which are these nice operators defined here with ASF. We are taking sum over the collection of cubes coming from the sparse family for the average of F over these cubes with the indicator function over these cubes. The boundedness of these sparse operators was initially discussed in several settings, and I've written down the result given by Moyne for p lying between 1 and infinity. So this is the boundedness result that we have for the sparse operators. In the two-weight setting, the boundedness of sparse operators or Bloom sparse operators was given in an earlier result of myself with Gong and Wu. So we do have the boundedness results for our sparse operators in the two-weight setting. Now let me define the Bloom sparse operators. So Bloom sparse operators associated to the symbol B and to the sparse collection S are denoted as TSP, and this is how we define the Bloom sparse operators for F that are locally integrable functions. The adjoint of the Bloom sparse operators is given by this T star SP. Here is the way that we define the adjoint of these operators. And now let me state our first result in this direction. This is joint work with Chen, Michaelesi, and Geely. And in this, we've shown that for P lying between 1 and infinity, lambda 1, lambda 2, some AP weights, and nu given by lambda 1 over lambda 2 to the power of 1 over P. We showed that if B is in the weighted VMO space with respect to the weight nu, then for every eta sparse family, for every eta lying between 0 and 1, the Bloom sparse operator is compact from the weighted LP lambda 1 space to the weighted weighted LP lambda 2 space. And the strategy that we implemented here is that we broke our operator into two pieces. We broke it into a piece which we call an essential part and a remainder term. We showed that our essential part has a finite range and our remainder term has a negligible norm. So we basically showed the compactness by showing the approximation in norm using the compact operators. And to show our result, we discuss the compactness of the adjoint of the Bloom-Sparse operator instead of the Bloom-Sparse operator, because showing the compactness of T star SP is same as showing the compactness for this by the result of Schauder. So here we consider our adjoint operator. We break it down into these two pieces, where, as I've said, this is our finite range piece, which is our essential term, and this is our reminder term T epsilon. So we to start the proof, consider some epsilon greater than 0, pick some n that is a large and some delta greater than 0. We fix a cube Qn of side length n such that the VMO properties hold on this cubes. So here, this is a condition that we assume. We say that the mean oscillations vanish if ever the length of cube is bigger than n, or if it's smaller than delta, or if the cube's intersection with Qn is empty. So this is how we consider our VMO conditions here. And we break our Bloom-Sparse operator into these four sums. So here, if you look at the way our summations are defined, here in the first sum, you have those cubes that contain Qn. So these can be considered as those cubes that have very large length, in which case you can use your VMO condition to bound this and make this have a negligible norm. In the second sum, you have those cubes whose intersection with Qn is empty, in which case you again you can utilize the property of B being in the VMO space, because now you're at a distance, a large distance from a specific point, a fixed point. In the third sum, you have those cubes that are contained in Qn, however, have very small length. Here too, you can use the property of VMO spaces to control the norm. In the last sum, you have those cubes that have length bigger than delta, however, are contained in Qn. So we argue that there are only finitely many cubes that appear in the fourth sum, making the fourth sum a finite range piece. So all of the other pieces, we use the property of B being in the VMO and the property that the mean oscillations vanish in here to show that the norm is negligible. And the fourth piece, we show that there are only finitely many cubes that lie that have a length that is less than delta and less than n. So greater than delta and less than n. So you show there are only finitely many cubes that satisfy this property, making the fourth piece of the summand here a finite range piece, hence compact. So using our result, we were able to show the sparse domination for commutators of Calden-Sigmund operators in the Bloom setting, because this was our principal motivation to study the compactness for the Bloom sparse operators. So let me define what Calden-Sigmund operators are in this setting of space of homogeneous type. And this definition again is similar to what one sees for the definition of Calden-Sigmund operators in the Euclidean setting. So here we say T is a Calden-Sigmund operator on a space of homogeneous type if T is an integral operator given with respect to a kernel that satisfies some very nice properties such as this. So you have the size condition where you have that the kernel is dominated, the absolute value of the kernel is dominated this way, and you also have the smoothness condition which says that if you perturb X or Y a little bit, then you still have a control over the kernel. So this is our description for Calden-Sigmund operators on the space of homogeneous type. And the result that we prove regarding this compactness is under the same hypothesis for P, nu, lambda 1, lambda 2. We say that if B is a locally integrable function on X and T is a Calden-Sigmund operator, the commutator BT is compact from the weighted LP lambda 1 space to the weighted LP lambda 2 space when B is in the weighted VMO space. So we obtain a similar result for the commutator of the Calden-Sigmund operator. We in fact also obtain the converse or the reverse direction here. So this is a small flowchart describing our strategy here for pursuing the proof. So we have B that we consider in the weighted VMO space. We show that for all sparse families, we have the compactness of our sparse operators, which we then use to show the compactness of our commutators of Calvin-Zygmunt operators, and additionally imposing a condition on the kernel of these Calvin-Zygmunt operators, we show that we obtain the reverse direction showing B belongs to the weighted VMO space provided our commutator is compact. This additional constraint that we put on our kernel, or assumption that we put on our kernel to obtain the reverse direction, is the non-degeneracy. So let me state what it is. So the non-degeneracy condition says that there exists some constant C naught and C bar such that for every x in our space, for y that lies in this annular region, we have a lower bound for our kernel. So this is what we say is a non-degeneracy condition for our kernel, and under this condition we obtain the reverse direction for our theorem. So under the same hypothesis where p is in 1 to infinity and nu is lambda 1 over lambda 2 to the power of 1 over p, with these being the AP weights, provided our t satisfies the non-degeneracy condition, and we now know that this is a compact operator from this in the two-weight setting, we deduce that B is in the VMO space. The proof of this is actually a very simple idea. So let me just briefly say a little bit about it. Let me say, I haven't written anything here, so let me just say what we do here. So the proof goes by contradiction. We consider a function B that, let's say, does not lie in the weighted VMO space. So when we say it doesn't lie in the VMO space, we have those cubes on which the mean oscillation for this symbol is a little large. On these cubes, we construct some test functions with disjoint supports. And when we look at the commutator image of these test functions, we obtain a sequence that doesn't have any convergent subsequence. So that contradicts the fact that our commutator is compact. So that's the strategy that we implement to obtain that the reverse direction, basically to show B is in the weighted VMO space. I haven't written that here because it's a little technical, the whole construction. But that sums up our work about Bloom's sparse operator in the linear setting, but whatever we did could also be extended to the multilinear setting. And just for brevity, I will discuss what our result is for bilinear Bloom's sparse operators. So a bilinear Bloom's sparse operators associated to a symbol B and sparse collection S is described here. So this is how we define the bilinear Bloom's sparse operator. And here we have the adjoint for the bilinear Bloom's sparse operator. And this is our result, which is a little more technical than what we had seen previously. Now we have P1, P2 in 1 to infinity, and we have a P that we describe from using P1 and P2 using this relationship. We consider our weights lambda 1 and lambda 2 to be in the AP1 class, and we consider W in the AP2 class. We construct a new dependent on lambda 1, lambda 2, and a W hat that is dependent on lambda 2 and nu. This is a relationship with which we obtained our result. So that's why we have these. And we've shown that if B is in the weighted BMO space, then for every eta sparse family, for eta lying between 0 and 1, the bilinear Bloom sparse operator and its adjoint are compact from these product in this product LP weight setting. So this is our result for the bilinear Bloom sparse operator. Since we have the bilinear sparse domination of commutators by the result of Lerner, Lorist, and Ambrosi, for bilinear Calvin-Zygmunt operators that are defined in this particular fashion with again a kernel that is very nice, satisfies the size and smoothness conditions that we had seen earlier. One can define these commutators. So here I've defined the commutators for this bilinear Calvin-Zygmunt operator. We could also obtain a result for the compactness result for the bilinear Calvin-Zygmunt operators commutators on these product LP setting. Again, this result is a little technical to state. We have all of these conditions where P1 and P2 lie in between 1 and infinity, and 1 over P is given by this relationship, and we show that this is our result. So this says that our commutators are compact on the product LP spaces in this weighted setting. Um, and the proof strategy, so one thing I would like to say before I stop is that, so typically a proof about compactness utilizes the Rees-Kolmogorov theorem to show that what we have is a pre-compact set. In our setting, in our proof, what is new, at least for the proof of the Bloom compactness of the Bloom sparse operators, is that we use the idea of approximating it using compact operators in norm. And this idea originally was developed by our co-authors Michael Lacey and Geely, where they tried to discuss the compactness of commutator of Rees transform, which we then extended and provided in the generality of space of homogeneous type for all the Calvin-Zygmunt operators. I think I would like to stop here. Thank you.
Thank you. Any question to the speaker? If no question, let us thank the speaker again. Our next talk will start in 2 minutes.